Hello everyone. Per your request, I would like to show you a video here answering some of the multiple choice questions that you had from the packet that I gave you in your preparation for your exam tomorrow. So we'll start out with number 1 here. We're taking the antiderivative of secant squared of x minus 2. And hopefully you remember that the derivative of tangent is secant squared, so the antiderivative of secant squared is going to be tangent. And minus 2x, of course, because the derivative of negative 2 is negative 2x. And we always have our trusty plus c for any constant that we could be adding out to the end. And if you look at your solutions, that looks like the answer is B. Okay, and that one's just knowing your antiderivatives. So you're going to get some tough ones, you're going to get some really simple ones just like that. Number 2 is one of those tough ones I was talking about. And it's really not too bad as long as you understand substitution and doing antiderivatives that involve reversing the chain rule. So if you look at this information, this is going to be important to finding our answer. But again, we're finding the antiderivative or the area underneath of this function from 0 to 2, which we don't even know what f is, so that's a problem. But we know that the derivative or the antiderivative from 0 to 8 of f is equal to k. So what we have to do here is we have to see that the derivative of x cubed is 3x squared. So if I choose u to be x cubed, then du is going to be 3x squared dx. Which you see here, we have 3x squared dx. So if we were to write our new, our new antiderivative, our new integral here, we get this. I replaced x cubed with u, and I replaced 3x squared dx with du. And everything else is exactly the same. The only thing I didn't change is I changed my boundaries for x here. X was going from 0 to 2. Now what I can do is I can figure out, well, what would u be going from if it were a function of u instead of a function of x? And this is the nice thing about substitution. If you do a substitution, you can actually change your boundaries as well so that you don't actually have to substitute back to the x's. So to do that, I chose u to be x cubed. So I can figure out my boundaries for u by plugging in 0 for x and x cubed and getting 0, and plugging 2 in for x and finding out that that would go from 0 to 8. All right, when x goes from 0 to 2, u goes from 0 to 8. And I just did that by plugging in 0 and 2 into x for my substitution. Well, look at this. If f of t dt from 0 to 8 is k, then f of u du from 0 to 8 must also be k. And so you get your answer. The answer is just k. Okay, and it's basically just a funky substitution that gives you the exact integral that they gave you in the first place. So your answer was D. All right, and like I said, as long as you understand substitution, this one's not too bad. Let's take a look at number 3. Number 3 is one of those easy ones, hopefully. This is the second fundamental theorem of calculus. We're going to take the antiderivative, then we're going to take the derivative, and so when you do that, you end up with the same exact thing. So you get the square root of x squared plus 3. But when taking that derivative, we'd have to chain on the derivative of the inside function, and the inside function being this x squared. So we'd have to chain on 2x. And that is all. And looking at the answers, we get that is C. Whoops. All right, very good. Number 4. All right, well, let me just talk about number 3 real quick, just in case you weren't understanding. We would take the antiderivative of this, which we don't know how to do quite yet. All right, but then what we're going to do is we're going to plug in x squared, we're going to plug in 0, and we're going to subtract. And then we're going to take the derivative of whatever we got. But essentially, if we're taking the antiderivative, then we're right back taking the derivative again. It's going to go back to exactly what it was. It's going to go back to exactly this, but instead with x squared in there now instead of t. And so that's why the x squared is in there. But when taking the derivative, this x squared would be something that we'd have to chain on its derivative to the end because we just plugged it in. And that's where the 2x comes from. Number 4 we're not going to do quite yet. It is something that we're not going to learn until chapter 5. So we're going to skip it. Number 5, you're going to have to follow along with the picture. but we're trying to find the value of a derivative from -3 to 4 of the function. And with the picture, there are 1, 2, 3, 4 different shapes that we have to find the area of. The first shape is a quarter circle with a radius of 2. So it's going to be pi times 2 squared over 4 because it's a quarter circle. And it's negative because it's below the axis. That's from -3 to 1. The second shape is a trapezoid. And this next trapezoid is positive because it's above the x-axis, but it has bases of 3.5 plus 2, and it's got a height of 1. So I can multiply it by 1, but I'll leave it at that. So I have this circle that's underneath the axis, this trapezoid that's above the axis. Then I have a triangle that's below the axis, and its base is 1/2. Its height is 1, and of course we divide it by 2, and it's negative because it's below the axis. And then we have another quarter circle that's below the axis with a radius of 1, and of course dividing it by 4 because it's a quarter circle. So now we just add up all these together. All right, this is going to be negative pi. This is going to be, let's see, 3.5 is 7 over 2 plus 4, 11 over 2, so it's 11 over 4. This is going to be 1/4, and this is going to be negative pi over 4. All of these have a common denominator except this first one, so I'll get a common denominator with that first one. And so that is -4 pi over 4. Adding them all up, I get -5 pi plus 10 over 4. And that looks like it is A. Okay, so that one's just breaking it down into areas that you can find. Number 6. We got to use the trapezoidal rule. We are allowed to use a calculator, so I'm going to go ahead and use that. So I'm going to put my function in for y1, and I suggest you do the same. X to the third plus 6x squared plus 10x plus 4. All right, and once I have that in there, I want to do the trapezoidal rule from 0 to 4. Okay, and I want 4 equal subdivisions. So if you remember the trapezoidal rule, what we need to do is we need to, it's 1/2, because that 1/2 comes from all of the bases being added together and divided by 2. And that divided by 2 gets that 1/2, times the height of each trapezoid, which is 1, plus f of 0, or I'm sorry, times the quantity f of 0, plus 2f of 1, plus 2f of 2, plus 2f of 3, plus f of 4. The endpoints we only need once, and everything else we need 2 of. That's the trapezoidal rule. And I would type that exactly into my calculator using my y1 command, because that makes it easier. So y1 of 0 plus 2, y1 of 1 plus 2, y1 of 2 plus 2, y1 of 3 plus y1 of 4, and I multiplied it by 1/2, and I get 296. 296 is C, and that's your answer. Okay, number 7, we don't know how to do quite yet, so we'll put that off. Again, that's something we're going to learn in Chapter 5. Many books put Chapter 4 and Chapter 5 together. Some do Chapter 5 before they do Chapter 4, or some of the things in Chapter 5 before Chapter 4. So again, we'll get to those things very shortly here, so don't you worry. I know that you're worried about getting to them. Number 8. What value of C on the closed interval from 1 to 3 satisfies the mean value theorem for integrals? All right. So the mean value theorem for integrals says that there is some value that equals the average value of the function, and you have to find out what that value is. So we'd find the average value of the function. To do that, we would do 1 over 3 minus 1 times the integral from 1 to 3 of f of x dx. Okay, that's how you find the average value. So this is just the area underneath of the curve. And what we're doing it is we're dividing it by the width of our interval. And that gives us the average value. Okay, so this right here is the average value. So when we do that, we get, let me type it in here. Approximately 1.2958. Now this is the average value. What the mean value theorem says is that there is some value, f of c, there is some c such that the value of the function is equal to the average value of the function. And we just have to find out what that c value is. Or in other words, we have to figure out what c is so that we could say that if we put c into the function, we would get the average value of the function. You can solve this graphically. You can solve this algebraically. Either way, it's fine with me. I'm going to solve it algebraically. So divide by 2 and then base e things, both sides. And when you do that, you get 1.91155765. And that is C. And there's number 8 for you. Number 9, I said not yet. I don't know why I put not yet. We can do number 9. But if you look at number 9, it is actually undefined on this interval from -1 to 0. So we actually cannot take the antiderivative because it's not defined from -1 to 0. So your answer is E. If you put in the cube root of -1/2, you would get 0 in the denominator. And so that's a problem. All right, so there's an asymptote there, which means this function is not integrable on the interval -1 to 0. So we don't have to do it. It's just E. Number 10. This is a good one. So we know that the function, the area underneath of the function from 1 to 3 is k, and the area underneath the function from 1 to 7 is -4. So we're going to take this information right here, and we're going to use it to find out what the area under the function from 3 to 7. Okay, maybe it's good to draw a picture. All right, and I don't know if this picture is right, but let's say that's 1, and let's say that's 7. And let's say this is 3 right here. We know that this area is K, and we know that the whole area is -4. So what would this area be then? Okay, only the area that we haven't talked about yet. Well, if the whole thing is -4, and this is K, then this area right here would just have to be -4 minus K. The whole thing's -4. If we get rid of K, it would just be this part. So this part right here is -4 to K. So the integral of f of x dx from 3 to 7 is -4 minus K. Now that's going to be important in figuring this out. Okay, this is, what is the integral from 7 to 3 of x plus f of x dx? Well, I don't like to look at it backwards like that. I'm going to change it from 3 to 7 and just make it negative. Okay. All right. If you ever presented with a problem where you're going from a bigger number to a smaller number, that's just backwards. Just flip it and make it negative. All right. The integral of x from 3 to 7 would be, let's see, this is going to be x squared over 2 from 3 to 7. So essentially I'm just doing this part first, and I'm leaving this part. I haven't done it yet. But if I put in 7, I get 49, negative 49 over 2 minus negative 9 over 2. So that would be negative 40 over 2 or negative 20. Okay, and then this, we know what this is. We just figured this out. It's negative 4 minus k. So with the negative there, it's going to be plus 4 plus k. And so what we end up with is we end up with negative 16 plus k. And that is E. Very interesting problem there. Okay. All right, and again, we had to use this information given to us here to figure out this particular integral. All right, from 3 to 7. And then from there, it was just using our knowledge of integrals to sort of manipulate this and then figure out parts that we didn't know and put them together with parts we did know and finding our final answer there. All right, number 11, almost done. So number 11, we are using this table to approximate using left-handed rectangles of equal width the area under the curve from negative 3 to 3. So from negative 3 to 3 is a space of 6. And we're using 3 rectangles. So each rectangle is going to have to be 2 long. Okay, each rectangle is going to have a width of 2. Whatever the height is, each rectangle is going to have a width of 2. So that's important. So if we're using left-handed rectangles, we need to know the height of the function at negative 3, at negative 1, and at 1. So what we're going to do is we're going to take f of negative 3 plus f of negative 1 plus f of 1. These are all of the heights. And if we multiply all the heights by the width of each of them, which is 2, this will be the area of all 3 of the rectangles added together. Now we have our calculator to help us with this. Even if we didn't, we could still do it. But so what we're f of negative 3 is 1.25, f of negative 1 is 0.53, and f of 1 is 1.04. Add those all together and times by 2. And you get 5.64. Uh-oh, I must have done something wrong. Oh, no, it's not. It's in there. It's C. Didn't see it for a second, but it's there. So C would be your answer for that one. Number 12, we have 100 cubic feet of water, but it's draining at a rate of 30 e to the t over 3 divided by 1 plus e to the t over 3. Now that's the derivative. It's the drain rate. So what we need to do is we need to take 100 cubic feet of water, and we need to take the antiderivative, the integral from 0 to 3 of that function, because this tells us how much is actually drained in the first 3 hours, because this is the rate at which it's draining. And if we take the area underneath of the curve from 0 to 3, that's how much it's actually drained in the first 3 hours. So if you do that, and you can use your calculator to do that, the math 9 function, typing in your function 30 e to the t over 3 divided by 1 plus e to the t over 3, comma x, comma 0, comma 3. And you want to do 100 minus the value you get when you do that. So that gives you approximately 44.18969. And that answer is B. All right, number 13. 13, it's important to know that the r of x is even. So it looks the same on both sides of the y-axis. And from negative a to from negative a to 0, it tells you that this area is 5. And for s of x, from 0 to a is -3, so we'll call this s of x. That area is -3, but this one is odd, which means it's symmetrical about the origin. So this area up here would have to be +3. And again, this area would have to be 5 because it's the same on either side here. So that's important into what we're going to be doing. And we're looking for the area from -a to a of 2s of x minus r of x plus 3. Well, I like to think of this as 3 separate integrals. First, the integral of 2s of x. And really, we're just looking at what is the integral of s of x, and then we can times it by 2. Well, s of x is, remember, this odd function, where we have an area of +3 under this one, area of -3 under this one. So total from -a to a, you have an area of 0. Times it by 2, and you get an area of 0. So this is going to be 0. Now we have to minus r of x. R of x from -a to a is this area plus this area, which is 10. So we minus 10. And now the integral of 3 from -a to a. And I want you to think about what that looks like. If this is 3, this is the function 3. And we're going from -a to a. And we're looking for this area. Well, it's a rectangle. We have a width of 2a, a height of 3. So we have an area of 6a. So, plus 6a. So we have -10 plus 6a for our answer. And that is B. And again, this is just understanding functions even and odd. It's understanding area. But that's it. Number 14, we don't know how to do yet. That's not going to be actually till like chapter 7 or chapter 6, one of the two. But it's not yet. And then number 15. 15 is we're using a picture to figure out area. So the graph of f(x) shown above consists of 3 line segments and 1 semicircle. Let g of x equal that function. Which of the following statements must be false? So we have g of x equaling the integral from -2 to x f of t dt. And the picture that they show you is f. So they're asking for the first one, g of 4 equals -2 to 4 f of t dt. So you'd have to find the area from -2 to 4. And what that's going to be is it's a quarter circle, a rectangle, and 2 triangles. And if you add those up, you get pi 2, 3, 4, 5. You get pi plus 5. So A is true. And again, we're looking for the false one. So we do not want A. B, g of -4. So for this one, we're looking from the area -2 to -4 f of t dt. And they say it's -pi/2. I'm going to switch it real quick because you know how I hate backwards integrals. So I switch the order and I put negative in front. So from -4 to -2, that's a quarter circle and a rectangle. The quarter circle has an area of pi. The rectangle has an area of 2. So it's -pi plus 2, which is -pi minus 2, which is what they had. So it's true. So we don't want B. Now we go to C. G prime of 6 equals 1, they say. Well, if g of x is the antiderivative of f of t, then g prime of x is actually just going to equal f of x. And that's the little graph that we have. So g prime of 6 is just going to be the value of f at 6. And if you look at f at 6, it has a value of 1. So this is true. So we don't want C either. D, we're narrowing down our chances. G of x has a relative maximum at x equals 4. So remember, g of x has a maximum when g prime of x goes from positive to negative. So if we want to know when g prime of x goes from positive to negative, we look at the graph. And we look at the graph of g prime. And g prime is just the graph of f. And f never goes from positive to negative. F is positive the whole time. So this is false because, well, just because g prime of x is always positive. So g of x is always increasing. So D is going to be our answer there. We can make sure by looking at E, g of x is a point of inflection at x equals 2. A point of inflection is going to occur when the derivative of g changes from increasing to decreasing or vice versa. And this is definitely true. At 2, g changes from decreasing to increasing. All right, so that's it for this. Happy studying, and I will see all of you soon. Have a great night.